Can you see the screen?
Yes.
Okay, perfect. Thanks. Well, hello everybody. I want to thank the organizers for inviting me to give this talk. Today I'll talk about the plausibility of super Eddington accretion to grow massive black holes at high redshift in particular. And this is a work I've done in collaboration with many people that are mentioned here in the slide. Just to start, I want to recap what also Zoltan said on Monday. Black holes are observed nowadays in two distinct populations. We have a population of stellar mass black holes that are distributed around a typical mass of 10 solar masses. And we know that these black holes form from stellar evolution at the end of the life of massive stars. And the population of supermassive black hole, typically living at the center of massive galaxies with masses above 10 to the 6, although there are some observations of also lower masses, but only for a few of these black holes. And unfortunately for this population of supermassive black holes, we still don't know the formation path, and many models have been proposed to date. One thing we know is that, according to the Zoltan argument, massive black holes grew during the cosmic history mainly via gas accretion. So what we typically expect is that the first seeds of these supermassive black holes could lie in the range between 10 to the 2 and 10 to the 4, 10 to the 5 solar masses. So in the range where now we are looking for intermediate mass black holes. That could be the relics of these initial seeds. But as you can see, we don't have observed this candidate yet. So it's important to understand how these black holes, these seeds could form and how they could grow. In particular, if we look at the high redshift population of black holes, you can see in this picture a selection of a subsample of the most massive black holes observed today at high redshift. You can see that they are already very massive when the universe was less than 1 gigayear old. So if we assume, for instance, that these black holes accreted at the Eddington luminosity for all their history, and if we go back in time, we can see that they should have formed with masses around between 10 to the 2 and 10 to the 4 solar masses. However, if we assume that they have grown only for part of the time at the Eddington luminosity, or for instance, at constant 0.5 at the times the Eddington luminosity, the constraint on the initial mass is much stronger. So we would need very massive seeds. So it's important to understand the initial mass and how the growth proceeded with cosmic time, because this could help us understand better also how it's possible to form these black holes. As I said, several models have been proposed. This just to recap the two main scenarios to date. There is the light seed scenario, where the black hole seed mass is below or about 10 to the 2 solar masses. And these are thought to be the remnant of the first population of stars, or also the black holes forming from the runaway merger of stars, or even stellar mass black holes in stellar clusters. So like the ones proposed by Porteges-Svart, or also Davis in 2012. On the other hand, there is also another class of seeds, the so-called heavy seeds, with masses already above 10 to the 4. And these seeds should form via the so-called direct collapse of massive gas clouds, via the formation of a supermassive star or a quasi-star. However, there are some open issues for both these models. For the light seeds, we need a sustained accretion at or above the Eddington limit for most of the cosmic history in order to explain the most massive black holes observed at redshift 6 or above. While for heavy seeds, we have to first avoid gas fragmentation, which we know occurs very quickly if we can form molecular hydrogen in the first halos. We have to efficiently dissipate angular momentum to transfer the gas toward the center of the halo. And we have to reach inflow rates of at least 0.1 solar masses per year in order to collect this large mass of gas in the center of halos to form a black hole seed with an initial mass above 10 to the 4 solar masses. So of course, because of these open issues, we don't know yet how these black holes could form, and we are still to study. So we need more detailed investigation. An alternative idea is that, of course, if we can exceed the Eddington limit, as also Yan-Fei just mentioned, this is observed in stellar mass black holes in the local universe. It also in tidal disruption events, we expect the Eddington limit to be exceeded. But this could also happen in the first black holes and also during when the black holes become massive. And indeed, in 2014, Madauart and Dotti proposed supercritical accretion onto stellar mass black holes as a way to bypass the difficulties associated to the light seed scenario in particular. You can see they took the model by Abramovic of a slim disk, of a radiatively inefficient accretion disk, where you can see that when you exceed the Eddington limit, the Eddington accretion rate limit, the luminosity tends to saturate at a few times the Eddington luminosity, and the radiative efficiency drops. And another peculiar feature of this model is that the dependence on the spin of the black hole, which is quite strong at lower accretion rates, becomes negligible. So in the super Eddington regime, the spin of the black hole doesn't impact the radiative efficiency of due to accretion that much. And from this work, and also from the work by Volonteri, Silk, and Dubus, we can then infer that in some condition, probably this supercritical accretion process is plausible in the universe, especially at high redshift when the gas is very dense and the halos that form first are quite massive. So what we did, and this is the first project I'll discuss, was to investigate in 2016 the plausibility of this accretion, radiatively inefficient accretion for the growth of stellar mass black holes in the typical environment we expect for massive galaxies at very high redshift. What we did was to assume a gaseous disk, a circumnuclear disk with 10 to the 8 solar masses embedded in a stellar background that could be the central stellar distribution of the massive galaxy. And we assume the population of 20 stellar mass black holes embedded in this gaseous disk, moving around. And this could be the relics of the first population of stars in the universe. We performed this numerical simulation with the hydrodynamic code Gizmo, including radiative cooling, star formation, supernova feedback, and reaching an extremely high resolution for this kind of simulation, which was 10 solar masses and a spatial resolution down to a fraction of parsec. Of course, we had to model the black hole accretion and feedback to follow the super Eddington phase. What we did was to assume that the black hole accretion rate was determined by the gas mass flux onto a sink particle that represents the black hole. And we also include the black hole feedback, assuming that the radiative efficiency was tied to the accretion rate as in the slim disk model by Abramovic. And the equation you see for eta is the fit provided by the Madau, Art, and Dot in 2014 that has a dependence also on the spin. You can see here a movie for the most accreting black hole we saw in our simulation. You can see the surface density of the gas. And now I'll start the movie. You can see this black hole moving through the disk. And then it's captured by a gaseous clump forming in the disk. And then it starts accreting. You can see that after a few mega years, the disk has been depleted from gas. And this is because of the supernovae that when start to explode, push away the gas and empty the region where the circumnuclear disk was. So I'll play it again. You can see this black hole that is moving through, then it's slowed down by the torques by these clamps, and then it's captured by the clamp. If we look at the evolution of the gas particles around the black hole, you can see here a snapshot of the distribution of a selection of particles as black dotted lines around the black hole. In red, you can see the black hole orbit in the XY and the XZ plane. And with the cyan part of the orbit corresponds to the phase when the black hole accretes at the rate above the Eddington limit. So you can see that the black hole is captured, it starts accreting above the Eddington limit until the clamp is disrupted. But the disruption of the clamp is not due to the black hole itself, but is due to the supernovae exploding after part of the clamp has been consumed, forming stars. And indeed, if we look at the mass growth history. You can see in the top panels the evolution for the super Eddington case simulation. You can see the red line corresponds to the most accreting black hole. And you can see the snapshot at 0.73 mega-year in the middle panel, and in the right panel, a zoom in the region where the most accreting black hole was. You can see that because of the lower radiative efficiency, when the black hole accretes above Eddington, its feedback is not powerful enough to empty the region around the black hole, and the black hole can continue to accrete. On the other hand, when we perform the same simulation assuming a constant radiative efficiency at 0.1, like the one used for optically thick, geometrically thin accretion disk, like the Shakura-Sunyaev model, you can see in the bottom panels that the growth is strongly suppressed, because as soon as the black hole starts to accrete, even above the Eddington limit, the strong luminosity produced by the accretion creates an empty bubble, which is quite large, and that completely stops the accretion for quite some time. So according to these results, we can see that the super Eddington accretion can help growing black holes from about 100 solar masses to even more than 1 order of magnitude in a few mega years, because of the lower radiative efficiency in the super Eddington phase. However, as Jianfei also mentioned, in the super Eddington accretion phase, also mechanical feedback is present, and this should be considered. This was not included in the paper by 2016, but more recently, we decided to include it in a more self-consistent simulation. You can see in this plot the radiative luminosity in units of the Eddington luminosity as a function of the accretion rate in the top panel, according to different simulations of super Eddington accretion disks by Zhang, Sadowski, Osuga, and McKinney. You can see with the solid line the fit by Madauart and Dotti for the radiative luminosity, and with the dashed lines the standard 0.1 radiative efficiency constant independent of the accretion rate. And you can see that despite the scattering in the data, the radiative efficiency tend to saturate, as also fitted by Madauart and Dotti. On the other hand, there is also a kinetic luminosity in the bottom panel that you can see is much higher than the radiative luminosity when the accretion rate is above Eddington, and this should be considered. So in the paper by Regan et al. 2019, we implemented the super Eddington power jet in the code ENSO according to the results by Sadowski and Narayan. We assume the flux accretion also in this case onto the black hole. In this case, we focused on an atomic cooling halo forming a direct collapse black hole seed, so about 10 to the 4 solar masses, and we followed the growth allowing for super Eddington accretion phases. We included the radiative feedback as in Madau 2014, and also included the mechanical feedback from the jet produced during the super Eddington phases. These are the results for two cases. When we launched the jet, because of the limited resolution, we had to assume a velocity for the gas ejected that is lower than the speed of light, because the code is not non-relativistic. So depending, we tried with different velocities for the outflow produced. In the left panel, you can see the 6,000 kilometers per second case, and in the right panel, the 100,000 kilometers per second case. And this is a function of time. You can see the density in the top panel, the density profile, and the temperature profile in the bottom panel. If you look at the top panel, for instance, you can see that when we start, there is a high density reaching the central part. The green region is the black hole accretion region. And as soon as the accretion rate exceeds the Eddington limit, there is a jet produced that suppresses the density around the black hole. And this can be seen around 49.7 kiloyears with the green curve in the left panel, but already at 21 kiloyear with the sine curve in the right panel. If we look at the temperature, this is also observed in the temperature. In the left panel, there is a quick temperature increase about 50 kiloyear after the beginning of the simulation due to the jet piercing through the dense region around the black hole, while this is more continuous in the 100,000 kilometers per second case, because the the intermittency of the accretion phase is higher. If we look at the average accretion rate, you can see here in the left panel how the accretion rate changes with time according to the different jet velocities we assume for the injection. Okay, thanks. And you can see also a comparison with the Eddington rate for the initial mass of the black hole we consider. You can see that even if we can exceed the Eddington luminosity, the production of the jet strongly suppresses the accretion for the next steps until the gas has time to come back to the center and starts a new phase of accretion. And on average, what we found is that the accretion rate self-regulates at about the Eddington limit, even when we allow for the super Eddington phases occurring. Of course, there is a limitation of the study. The time we consider is only 100 kilo-years, so it's quite short, but this is because the simulations were very expensive. And it's also possible, and what we saw is that the typical timescale for the gas to come back is the free fall time of the gas around the black hole. So this means that even if this jet is produced and is able to stop the accretion for quite some time, as soon as the gas has time to come back, a new super Eddington accretion phase can start, and this jet is not able to propagate outside the halo and produce very strong outflows. So it's only a local effect around the black hole. And so what we think is that if more gas is able to come in with time when the halo grows more, it could be that the free fall time gets shorter, and then even this jet could not propagate outward that much, and the super Eddington phase could continue unimpeded. Of course, this work had some limitation. This is the summary of what we found. Of course, the low radiative efficiency of super Eddington accretion phases prevents clumps and gas from being pushed away too much, unless the jet launched in the mechanical, by this mechanical efficiency pierces through the central region. And so we need for massive dense clump, massive halos with a very dense gas, so that the dynamical time scale is quite short and we can avoid this suppression of the accretion rate. Of course, there are many issues because of the highly idealized setup, the short time scale of the simulation, and this is why we want to move to self-consistent cosmological environments. So the idea is to start from the simulation we published in 2019 of the cosmological evolution of a massive halo at redshift 6 with self-consistent non-equilibrium chemistry, state-of-the-art star formation supernova feedback processes, including radiative transfer, and also the self-consistent evolution of the black holes, including super Eddington accretion. This is a summary of the models we are including. And just to conclude, this is the results of our previous paper, where the accretion rate onto the black holes was limited at the Eddington rate. You can see in the left panel with the red line the growth of the most massive black hole in the simulation, and with the blue dashed line the accretion rate in units of the Eddington accretion rate. And of course, we applied the limit, so you can see that we cannot exceed the Eddington accretion rate. But there is a phase between redshift 10 and redshift 8 where the accretion rate is almost constant at the Eddington limit. And indeed, if we look on the right, where we measure the instantaneous accretion rate without applying the Eddington limit in blue, you can see that there are many phases when the black hole accretes at much higher rates than the Eddington limit. So the goal for the next work we are performing now is to study what happens when we allow the black hole to accrete at super Eddington rates and mechanical and radiative feedback is produced by this black hole in a self-consistent cosmological environment. Thanks.